I hope you can see the shared screen.
Yes, sir.
Yes, sir.
Okay. So in this course that is LiDAR technology, we are going to discuss about fundamental concepts, working principles, and applications. Okay. Uh, so LiDAR is one of the remote sensing techniques, and we have already briefly discussed about it previously. So before discussing the fundamental concepts of LiDAR, first I would like to discuss about the background. Okay. Before the invention of LiDAR, that stands for light detection and ranging. Okay. Before its invention, what are the technologies which were available and which were kind of fundamental blocks to design the LiDAR technology? Okay. So first we'll discuss about the fundamental techniques, their working principles, and how they are combined together to realize the working concept of LiDAR. Okay. So as you see in the slide, in figure A, in a three-dimensional Euclidean space, a point P1 is located. Okay. And if I ask you to characterize the geometrical property of point P1, so how it could be done? First of all, you need to know about the coordinate system. So first you define the coordinate system. Okay. And though you are going to characterize the geometrical property of this point, it means you want to locate it, okay, in a 3D space. So once you define a coordinate system as it is shown in the figure, the three axes are defined, x, y, z, and the location of origin is defined. So we have already discussed previously how to define a coordinate system. So once the coordinate system is decided, to locate a point P1 in a 3D space, you need to calculate if you project a point P1 on XY plane and on the Z axis. So what will be its value? Okay. So if you project this OP1 vector on the Z axis, so it will give you idea about the Z coordinate value. Okay. So let's say if we try to understand it from the vector algebra concept. So like unit vector you need to define. So along X, let's say if I, along Y, J, and along the Z axis, it's K. So unit vectors are generally defined the direction of the line. So I, J, K, they are defined. So once you project vector OP1 on Z axis, it means it is giving you the coefficient value of unit vector K. So what is the amplitude of that component? That will you get. Then further to get value, projection value of vector OP1, its component on y-axis and x-axis, what you need to do? You need to further project is on xy plane, and then you need to calculate what is the orientation of that projected line on xy plane from y-axis and x-axis. Okay, it means what is a projection, what is a deviation, angular deviation from unit vector I and unit vector J, which are along x-axis and y-axis respectively. So if you see the formula that is written over here, so x1, y1, z1, they are computed. And for the computation of these three components, you need to know what is a distance from point O, that is origin of a coordinate system, to point P1. So that range R should be there. Okay. And in addition with that, you need to know orientation of this range vector OP1 from Z axis as well as in a horizontal plane, either from Y axis or X axis. So two angles are required and the range value is required, that is giving the distance from origin O to point P1. Okay, so either way, the point P1 can be located in the 3D space. Fine. So this is the way we do the geometrical characterization of a point. Okay, so now you have a background how by using vector algebra and coordinate geometry the point P1 can be located and what are the raw informations which are required. So in this case, if we start from calculation of angle and range, so to calculate position of point P1, the range R and two angles are required. Can we locate a point in a 3D space using uh, remote sensing instruments? Yes, we have the traditional equipments by using which you can do it. I think all of you are familiar with electronic distance measurement instrument, EDMI and theodolite. So all of you have, okay, total station, I think you have already used. Total station based experiment, virtual experiment, I think you have done it in the previous semester. So the working of total station is combined with the working of EDMI and theodolite. Okay, so EDMI is the electronic instrument that is used to calculate distance between 2 points. So here, if you want to calculate range R, then you need to place EDMI instrument at origin O. Okay, so if we see the internal electronics of EDMI, so there is a laser source. That laser source fire the laser beam. Okay, it hit the target, then returned back. If you do this analysis over here, so if you if you place the EDMI instrument at origin O, okay, and you initialize it, the first laser beam is fired. Okay, it goes to the point P1, that is a target point, and it is further reflected back to the source from where the laser beam is fired. Okay, so by analyzing the total time of travel that I will discuss later, by analyzing this entire process, okay, the information that is gathered is how much time is taken by a laser beam from laser source to target and back to the laser source. Okay, that total time is recorded by the internal component of ADMI. One point you need to remember over here, when the laser beam is fired, we consider particle nature of light. So this light travels in a straight line. Okay, so when the laser beam is fired, you are considering the particle nature. So you are already uh, using that concept, like it travels in a straight line, goes to point P1 and return back in a straight line. So same path is further traversed in a backward direction. It means the total distance that is covered by the laser beam is from OP1 and back to P1O. Okay, that is 2 times of range R. So that is a total distance covered by the laser beam once it is fired from location O. Okay, so in this way, once you have a total time of travel, so how much time is taken by a laser beam from point O to P1, then back, it is traversed through the same path, P1 to O. So if you divide it by 2, it gives you how much time is taken by laser beam to travel from point O to P1. And you know that laser beam, it travels with the speed of light. So if you divide it, the total time divided by speed of light, it gives you the, what is the range, what is the distance from O to P1. This is a basic principle through which the range is measured using EDMI. Now we have another instrument, that is theodolite. This theodolite is used to measure the angle from a reference line. Okay, so it is used to measure the vertical angle, that is alpha over here, as well as the horizontal angle beta. If you combine the principle of the working principle of these two, EDMI and theodolite, it gives the working concept of total station. Okay, so we can say that total station is a combined having combined principles of EDMI and theodolite. So it is comprised of EDMI and theodolite. Okay, but let's say if our aim is to get coordinate of entire object. Let's say if you want to model entire object, I'm talking about 3D modeling. Let's say you are interested in modeling of trees, you are interested in modeling of buildings, similarly other objects. Okay, so to geometrically represent a building, obviously you need to have a dense points coordinate information from the building facades, building roof, even interior of the building. Then only you can represent the different surfaces from the building. Similarly, if you want to geometrically represent a tree, then you should have a dense point coordinates from various points which are captured from the tree. Okay, can we do it using total station based data acquisition? As you see, I am mentioning over here, we want to represent entire 3D structure of the object. Principle is same, like that entire object, what you need to do, let's say if I consider the building, so building has a 4 facade, 4 sides, 1 roof. Okay, if you want to generate a 3D structure of a building and further you want to do the modeling, so what you need to have, obviously first you need to define a coordinate system. In that coordinate system, you should have points coordinate from the 4 sides and rooftop. Okay, let's say if you consider one side of the building, so though it is planar, but there are windows and some other substructure. So what you need to have? You need to have, first you need to identify the various points, target points on the building facade, and you need to compute their coordinate for the modeling. Okay, and if you want to do it using total station, can it be possible? Jasri, can you give some idea about it?
So to model a 3D figure, as we are using, as you said that for this example, if we use the total station, it will be of fixed it is placed at fixed place, but we should measure for 3D figure. So I think we can't.
See, okay, 3D figure means just see representation of object in 3 dimension. Meaning is that how you can represent object in 3 dimension. First of all, the geometric information from that object should be acquired in a particular coordinate system. No?
Yes, sir.
When we see the object, like can you have a 3D sense of an object if you look the object from the moving train? No. But if you sit somewhere and if you look towards the object, you have a sense of 3D.
Yes, sir.
Okay. So because you are just analyzing that object in your reference frame.
Yes, sir.
So similarly, first of all, what you need to do, you need to fix a coordinate system. Okay. And in that coordinate system, the way the point P1 coordinate is calculated, if you want to exactly model the four sides of building, roof of the building, so what you need to do, let's say if you select one side of the building, let's say it is 4 meter by 6 meter. Okay.
Yes, sir.
So that 4 meter by 6 meter of the surface, on that surface, you need to select a uniformly distributed target points, so that once their coordinate you can calculate, you can mathematically generate a surface that can actually represent that building site.
Yes, sir.
Getting the point?
Yes, sir.
Similarly, if we consider a tree, and if you want to have a 3D structure of a tree, so you know that tree is made up with two basic component: crown section and trunk section. So trunk is
Yes.
a kind of cylindrical object, while the crown is volumetric object. So what you need to do, 360-degree all sides, and if you just try to see, the crown is a kind of envelope.
Yes,
So
sir.
over that envelope surface, you need to identify the uniformly distributed target points, so that if you calculate their coordinate in a reference system and if you model it, so they will actually give you idea about what is the outer outline, what is the outer surface of the tree crown.
Yes, sir.
Okay. So that you can able to estimate what is the volume of tree crown, what is the cross section, okay, and what is the vertical distribution. So
Yes.
if you okay, fine, you can mute. So in the same way, if you want to do it using total illustration, what you need to do, let's say there are for a tree representation, uh, as I have been discussing, like you need to select a target points, and therefore, and if let's say to represent a geometry of tree, the required target points are nearly let's say 10,000. Though it is not up to that level, let's say it all depends on how dense you are acquiring the point cloud. So let's say it is 5,000. Okay. So 5,000 uniformly distributed target points you need to select from a tree for its geometrical representation. If you want to operate it, if you want to get coordinate of 5,000 points using total illustration, 5,000 times operation you need to perform. As you see, it is written, the total illustration needs to be initialized for each measurement. 5,000 times you need to click the TS, one time, one measurement. So it is not very feasible solution for that. You need to have a kind of instrument that is once you initialize it, it automatically target all those 5,000 points without the user inference. Okay. So here LiDAR comes into the picture. Light detection and ranging technology that is there in the LiDAR systems, LiDAR instrument. So by using the LiDAR instrument, the dense point cloud from the object for its geometrical representation can be acquired in very short period of time. Okay. So the LiDAR is used to collect topographic data, mainly the geometrical data, with the speed of light. Okay. And geometrical as well as radiometric information of the topography are acquired using LiDAR. This technique is complementary over the other remote sensing techniques, and it eliminates the many limitations that we will discuss. So as I have discussed about the TS based operation, so the data acquisition using terrestrial surveying technique uh, that is having the combination of total station and GPS, this is very labor intensive and time consuming. Like in the previous case I discussed with you, 5,000 points are there to represent a tree. So 5,000 times operation you need to perform. And we have other remote sensing techniques as well, like photogrammetry. In the photogrammetry, you get a photograph, and that photograph has a radiometric representation of the object. And obviously in the photograph, you will get XY coordinate of a pixels. But if we consider a tree, and if you click the image of tree from the top, can you get information about object or other details underneath the tree?
No, sir.
Okay, so in case of photogrammetry, you will not get the depth information. If we consider data acquisition from a tree, and let's say data is acquired by the airborne platform, so you will get only the information about top of the tree. Okay, so that's why it is in case of photogrammetry, it generally do not cover the region under the canopy. But LiDAR, though in LiDAR we use a laser beam, just like electronic distance measurement instrument. So that laser beam can penetrate through the canopy and it can reach to the ground. Okay, so this is the benefit of LiDAR. So like in case of EDMI, we discussed about it is comprised of laser source. Okay, and that EDMI component is there in LiDAR. Okay, so that laser source, first of all, you need to understand how the laser is generated and what are the properties of laser which we use in case of LiDAR or EDMI. So laser is an acronym and it is defined as light amplification by stimulated emission of radiation. Okay, and through this process, the generated laser is considered as highly monochromatic. It means the energy generated at a fixed wavelength. It is coherent. It is sharply focused and directional, so that once you fire a laser beam, it goes to the target and hit the target point. There should not be much spread. Okay? Like a laser pointer when we use for the presentations. So our point as a pointing device, if you point somewhere on the screen, okay. So if you see that the diameter of laser, okay, once you switch on it, the laser footprint is projected on the screen, and that has a size bit larger than the diameter from where it is generated. So that is due to the spreading in the medium once the laser travels through that. So here, what is the requirement in case of EDMI as well as LiDAR? That laser source should be directional and sharply focused. Here you can understand how the laser is generated. So what happens to the external source, that at an atomic structure, the laser source is excited. So a photon interact with the atomic system in its upper state. Okay. Then what happens? Due to light amplification, it's a stimulated emission to the light amplification. So what happens? The photons from the excited state is driven down to the lower energy state, and there is energy difference h nu, that is E2 minus E1. So what happens?
Excuse me, sir.
Yeah.
Sir, are you displaying anything?
Sir, screen is not being shared.
Okay, fine. Thanks for pointing out this. Yeah, thanks, Sumit. Okay.
Yes, sir.
Okay, I hope you can see now.
Yes, sir.
Okay, fine. So the discussed content is not much related to the, the displayed content. So obviously, I already explained about it. So in this case, like the uses of LiDAR and why we prefer it. So one point that I discussed earlier, like if we consider the photogrammetry, and if you acquire the images using aerial platform, so if we consider the trees, you can't get the information below the tree canopy. Okay, below the tree crown, you can't get the information. Images are only collected from top of the tree. But in case of LiDAR, as it includes the EDMI, principle of EDMI, it has a laser source, and its working is based on calculation of total time of travel. So that laser beam can penetrate through the tree canopies, okay, and it reaches to the ground through the canopy and return back. So if we compare the working of LiDAR and photogrammetry, so for the forest related applications, okay, the LiDAR is preferred over photogrammetry, because in case of LiDAR, you get information from the terrain or from the objects below the tree canopy. Okay, that principle will be discussed in detail. So as I have been discussing, in the LiDAR, we have electronic distance measurement instrument that is working on that principle. So we have the laser source, okay, and the laser source is selected on certain basis. So the acronym of laser is light amplification by stimulated emission of radiation. So that process will be discussed later. So the generated laser beam, okay, that should be highly monochromatic. It means it should be generated at the fixed wavelength, and it should be coherent, and we consider it highly sharply focused and directional, so that if the target point should be focused. Okay, so once from the laser source a laser beam is fired, okay, And that you can understand from the pointer that we use while the presentation to just show the different text. So if you see how that laser pointer work, so once you switch on, so from the circular cross section, light is emanated. Let's say if you are using green laser, so green light is emanated. And finally, its footprint is projected on the screen. If you analyze it, so the size of diameter through which that green laser is emanated, and once it is projected on the screen, though that green color circle that will be there on the screen is bigger than the size of this laser pointer through which the laser green laser is generated. It happens due to the dispersion in the medium. Okay, laser dispersion in the medium. So we need to select laser in a certain wave band, okay, such that the dispersion should be least. Why it is so? Because see, if we consider over here in EDMI, it has a laser source, as I discussed. Once you initialize the instrument, the laser beam is fired. Okay, and our target is point P1. So this is a very pointed location. It's a point. And how we define a point, we can say area tends to 0. So to locate the exact point, the footprint size should be, the area footprint size should be nearly 0. Then we can say it is pointed. So this is the reason why we are interested in a point-based analysis. It's not a pixel, like if you consider the image-based studies, okay, that we have done previously. So there we discuss about a pixel with respect to the spatial resolution. So it has a certain area for which we assign a DA number. While in this case, we have we have a point, and that the coordinate of that point we are calculating. So this is the reason why the laser that is generated by the laser source should be directional. Why it is directional? Because once we target in a certain direction, it should follow that. Okay, and it should be sharply focused so that a point coordinate can be ensured. So the laser generation principle, you need to excite a laser source at its atomic level, and then what happens? A photon that is at a higher state goes down to the lower state, and the energy difference that is created, that energy difference is responsible for generation of the second photon. So by one photon, you are just exciting the internal atomic structure, and two similar photons are generated. In this process, the two photons which are generated by triggering, by using a triggering principles by an external atomic, external photon, the two generated photons should have same energy, same direction, phase, and state of polarization. Further, two are generating 4 to 8. It's a kind of chain reaction. So using the laser source, we generate two types of laser beam. The first one is a pulsating laser, and second one is continuous wave laser. First, we talk about pulsating laser, where at a certain interval, this kind of laser pulse is generated. So if you see in the diagram, first you need to understand how we can define a laser pulse. Okay, so it seems Gaussian in nature, and certain points are marked over here. So this pulse laser, it is represented on time and amplitude axis. And when the peak is attained, it is represented by 100%. We have a 2 level at 50%. Okay, so if you see the rising side and falling side, on both sides at a 50% level, if you see the time difference that is represented over here by TP, it is called as pulse width. And this is one of the important parameters that we will be discussing further. So the definition of a laser pulse, defining the laser pulse, the pulse width is one of the important parameter. Okay. And in case of LiDAR, the pulse width which we consider, it should be around 10 nanosecond. It is a general specification. Nowadays we have advanced equipments, LiDAR systems, where we use where we operate the instrument at a different pulse width. But in general, it is selected 10 nanosecond. Okay. And we have a different types of lasers, like diode pumped solid state lasers and Diog laser. Okay. The second important parameters related to the laser pulse is rise time. So rise time means the time taken by a laser pulse to reach its 90% level from the maximum to its 10% from the maximum. Okay. And it is generally kept low. So as you see in the figure, it should be 1 nanosecond. And by using 10 nanosecond laser pulse and 1 nanosecond rise time, you can obtain a ranging accuracy of 2 to 7 centimeter. What happens over here? Like if I again go back to the first slide, as you see, at location origin O, laser source is placed. You switch on the device. Okay. To the stimulated emission by using a triggering photon, laser pulse is generated. Okay. And that laser pulse leaves the transmitter. Okay. It goes into the medium. It travels in a straight line. As we have defined, it should be directional. So the direction towards which we have focused the laser source, it goes in that direction in the straight line. It finally hit the point P1. Okay. Returned back to the same path, and it is further received by the instrument receiver. So laser source is a part of transmitter, and we have a receiver unit to sense the return. Okay. So I hope you can correlate all these discussions in one point, that how this EDMI operates. Okay. Now here I'm talking about the accuracy that we get.
Sir, one thing I have to ask.
Yeah, please. Can we discuss later? Can we discuss later on?
Yes. Yes.
Yeah. So the ranging accuracy will get 2 to 7 centimeter. So could you try to understand? Could you try to figure out on which parameter this ranging accuracy 2 to 7 centimeter depends? So just keep in mind, like on what parameters this ranging accuracy 2 to 7 centimeter depends. Okay. That point I will clarify over here. So now you can see in the figure, this is there is a LiDAR instrument. And I think you can identify the tripod. The yellow color tripod is there. On top of that, this LiDAR instrument is mounted. Okay. Once you switch on the instrument, it continuously fires the laser beam in a different direction, covering the horizontal and vertical profiles both. As you see on the terrain, okay, the white color circles represent target points. They are the various target points, and their coordinates are acquired in the internal coordinate system of LiDAR system. Okay. And below that, you can see a pulse laser diagram is shown. So it is shown purely square pulse, but generally we do not get a square pulse. It is like the shape discussed previously. It's Gaussian, where we have two parameters, pulse width and this that is rise time or fall time. Okay. Now in figure B, once you it is the working principle is explained. Once you switch on the laser scanner, it starts firing the continuous laser pulse as shown in the diagram in figure A. At a certain speed, after switching on the device, LiDAR system, it starts firing the laser pulse in a different direction. So different direction means not at a particular point all laser pulses are hitting. What happened when one laser pulse is fired? The orientation of that laser source changes to some adjacent target point. And the scanning can be done either row wise or column wise. Okay, if I define over here in this figure, the horizontal line, if I say it's row wise, and vertical line, if I say it's column wise, so scanning is performed in that way. So horizontal profile and vertical profile. But when we consider one target point and doing the analysis, what are the raw parameters which are estimated from one target point? Let's say this P1. So at a particular time T1, laser beam is fired. That is a laser pulse. Okay, it travels in a straight line, hitting the target point P1. You need to focus in figure B. Okay, hitting the target point P1, and further it follow the same path, traverse back and received at the receiver. The information that is recorded within the this transceiver unit, within the laser scanner, we have transmitter and receiver both. The transmitter unit is comprised of laser source, and receiver unit is responsible to sense the return energy signal. Okay. So there is an internal counter circuit as well. That I will discuss this architecture in detail later on. So that counter circuit is responsible to measure the total time taken by a laser pulse from laser source to target and back to the laser, back to the receiver. So the T, total time of flight, is recorded. If you divide it by 2, it gives you the total time taken in one side from laser source to target. And if you multiply it by speed of light, it gives you the range. Okay. Range means which parameter you have calculated. In the first slide, this range is estimated by EDMI by simple mathematical manipulation, where the time recorded by the counter circuit is used and it is multiplied. Half of it is multiplied by the speed of light. Okay. Now we have once the coordinate system, the XYZ coordinate system that is mentioned in figure A, we have defined the XY plane and Z axis. To locate a point P1 in a 3D space, you need to calculate two angles as well, alpha and beta. Okay, as I have discussed previous in the first slide. So these two angles, alpha and beta, are recorded by the theodolite principles, and there are internal angle encoders. Those angle encoders measure the direction of fired laser beam from Z axis as well as either from X or Y axis. Okay. So once you initialize the instrument to the internal mechanism, no need to do further. Just switch on the device. It will start and it will further scan the entire surrounding. Okay. It's not like totally station-based operation. Like for each measurement, you need to initialize the instrument. Initialize once at a certain interval. Just you see the first laser pulse, second, third, fourth, and further remaining laser beams are fired in a different directions. Just you see those points are uniformly distributed on the, generally we consider they are uniformly distributed because the angular separation are uniform. Once the first laser beam is fired, second fired, third fired, if you see the angular separation, that is constant. Okay. Fine. So there was a query from any one of you. What was that?
Sir, I was asking that when a laser beam is fired, it is fired from transmitter, then how it will be reflected back, sir, when it is got struck by some anything, means when it is struck by anything, when it detects, and how it gets to the exactly receiver point. That because when we are using the laser, we are using a directional monochromatic and well focused, then when a laser light is emitted from transmitter and just will be reflecting back, then it will be reflecting back on to the same path which it has traveled, then how it will be sensed by the receiver.
What we have taught in the remote sensing course, like light coming from the sun. Okay. It is reflected by the target. So once that light interact with the target, what happens? There are three components: the reflected, transmitted, and absorbed. Okay. So there we have one reflected component. And there we discussed about types of reflection, whether it is specular or diffuse. I hope you can recall that discussion.
Yes, sir. Yes, sir.
So we have the reflected component over there.
What, sir? Please.
No, if you recall the previous, see, once you fire the energy beam, na, that laser
Yes,
pulse,
yes,
and
sir.
once it interact with the target, okay. So after
Yes, sir.
interacting with the target, what happen if you apply the law of conservation of energy? So where that energy goes, okay.
It's in three
So what?
modes.
Yeah, that is that the same concept you can apply. We have a transmitted, absorbed, and
And
reflected.
reflect. Yes, sir.
Okay, if it is a solid surface, so we barely have a transmitted component. So mainly we have absorbed and reflected component. And just see,
Yes,
this
sir.
laser beam is very sharply focused. Okay, so there is a reflected version, there is a reflected component, and that reflected component is sensed in its own field of view by the receiver.
Okay, sir.
Okay. So
Yes, sir.
we'll do the detail analysis. See, this is an introductory concept, so I'm not discussing in very detail. We'll see it. What will be the changes shape of the laser beam? Once
Okay, sir.
you have a specific shape of a transmitted laser pulse. Once it is received, how the shape of the received energy changes with respect to topology of the target point, a topology of the surface where target point is located. So that level of analysis also will perform later on. So though this is an introductory discussion, so I'm not going in depth. Fine. But it's a good a good point you raised. Like it's a very obvious question. Like when a laser beam is fired, okay, how it travels the same path, okay, how it is sensed at the receiver. So it is due to the reflected energy component. Okay, so this LiDAR principle, it is based on the time of flight, that is the measurement of range using the laser source. and where we calculate total time of travel. It is divided by 2. And when the laser travels in medium air, so we consider it travels with the speed of light. So by using this simple formula, that is distance traveled by a laser beam from laser source to target is equal to C into T by 2. So the principle of LiDAR, it came into the existence and it is known since 1960s. And all the electronic distance measurement instruments, EDMI, they work on this principle. So we have various types of LiDAR systems. As you see in the figure, the classification is done on the basis of platform which we are using to install the systems. In the first two case, if you see, it's on top of the vehicle in a closed case, various sensors are integrated. You can see there is a GPS antenna, there is a camera, there is a laser scanner. It is called as mobile laser scanning system, and it works on the principle of LiDAR. Okay. And additionally, we have a photogrammetric sensor as well, that is camera. Okay. So this entire, the unit that is mounted on the car, okay, it can be further mounted on the vehicle that runs through the railway track. So this operation is also called as mobile laser scanning for the railways. The first one is used for road and highways. In the third case, it's a static operation. The laser scanning is not performed using a dynamic moving platform like in first two cases. It is called as terrestrial laser scanning, where on a heavy duty tripod, a lightweight tripod, you mount a LiDAR instrument, you switch on the device, it will collect the data in its surrounding. So the platform is not moving in this case, it's a static platform. So these three are the ground-based operation. Mobile laser scanning through road and highways, mobile laser scanning through railways, and terrestrial laser scanning. All these three systems are operated, and they are the ground-based LiDAR systems. We have aerial systems as well. When you mount the integrated unit, the LiDAR system on the aircraft, the operation is termed as airborne laser scanning. You can also mount the LiDAR system on UAV. It is called as UAV LiDAR. So this categorization of LiDAR system into various categories are done on the basis of platform used to operate the systems. Basically, the fundamental concepts and working principles will discuss in the context of airborne LiDAR. So airborne LiDAR will consider as a base LiDAR system to discuss the working principles and fundamental concepts. So this is a new technique, airborne altimetric LiDAR. And this airborne laser scanning, the LiDAR system that is used for that is known by different names. Okay. It is called as airborne altimetric LiDAR, laser altimetry, laser rangefinder, laser radar, laser mapper, etc. And the data that is acquired, that data represent the 3D view of the area, a 3D view of the scene from where data is collected. Further, you can assign the actual RGB color to the LiDAR point. Like in this case, as you see that the camera unit is also integrated with the LiDAR. So what happens when the LiDAR fires a laser beam and it calculates through the processing, further processing, if a coordinate of a point is calculated, Same point color information is also collected through the camera. Data collected, photograph collected by the camera. Okay. So corresponding to a particular point, we have its coordinate, as well as we can also have its RGB value. So this is very detailed information about the scene. We are getting geometry of the point, we are getting the actual color of the point. Further, you can also have an analysis of the reflectance of the point, the intensity, how much energy is reflected back. Okay. Once the laser beam is hitting the target, how much energy is reflected back, that uh, that is also recorded, okay, in terms of intensity. So point from where the laser pulse is reflected, the target point P1 is characterized by its coordinate, its reflecting capability, its RGB value. Okay, so very detailed information we get by using LiDAR systems. We can also do the LiDAR systems classification on the basis of other parameters, like whether it is a three-dimensional LiDAR or 2D LiDAR, whether it is based on the pulse, laser pulse, or continuous wave laser. Okay. So we do the classification on the basis of platform, whether it is ground-based, aerial, it is dynamic, static. Okay. Then what kind of LiDAR instrument is used, whether it is three-dimensional or 2D. We'll discuss about the differences in 3D LiDAR laser scanner and 2D laser scanner. So laser scanner unit is a part of, is one component of LiDAR system. When I say LiDAR system, it's not a laser scanner. Okay. The LiDAR system is an integrated version of various sensors, where laser scanner is one of the sensors. Okay, so we have 3D and 2D laser scanners. Then further, the laser source, which is inbuilt with laser scanner. What is the working principle of that laser source? Whether it is pulse based, I have already discussed, a pulse laser is generated. There is also a generation of continuous wave laser. Okay. For this time, you need to just remember it. And the differences between pulse laser, continuous wave laser, their working principles will be elaborated in very detail in unit second. So the first terrestrial LiDAR, it is mainly work on phase-based and pulse-based laser scanner, while the rest of the two are mainly based on the pulse-based. Now in this slide, you can see the 3 dimensions. It's not a, it's a 2D version of a 3D view, we can say, for data acquired by various types of LiDAR systems. In the first case, it is the data is collected by mobile laser scanning through the road, and the color is not an actual RGB value. The color is assigned on the basis of color given to the point on the basis of its height. Okay, so if you see that the lowest point, this blue color, and the highest point is red color. So on the basis of height, the colors are assigned, and you can clearly identify the structure of various objects. It's a point cloud. What will happen? It's not like a pixelated version. Like in images, if you zoom them, you will have a pixelated version of image. While in this case, what will happen? You will just see the points once you zoom in. Okay, and there will be a gap between the points. So it's a point cloud version of the object. Okay, but geometrically, you can identify them. Similarly, in the second case, data is acquired along the railway track. Third case, just see, this is a color coded point cloud. It is acquired by terrestrial laser scanner. It's not image. It's a point cloud where each point has its original color. Okay. So if I consider the point P1, so point P1 has its coordinate X1, Y1, Z1, and its RGB value. What is color of that point? Okay. Similarly, in the fourth case, the data is acquired by the UAV LiDAR. You can see that the buildings are there, vehicles are there, trees, shape of the trees, you can see. And in this case, the data is acquired using airborne laser scanning. The point density is less compared to other LiDAR systems because in this case, it is operated at higher altitude. So you can see the first figure, it represents an industrial area and water canal over there. While in the second figure represent a forested, this forested mountain. So like going through the representation of data sets which are acquired, just you can see like when you have these kind of data, how much information you can collect from these data. That quickly you can decide based on the background and various courses which you have gone through in the first semester.